Welcome to Tomorrow Unveiled. So, this past week in artificial intelligence.
Mm.
Wow, it wasn't just busy, it felt, I don't know, different. Seismic, maybe?
Yeah, seismic is a good word for it. We're definitely not talking about just, slightly better models this time.
Right. That whole era of just scaling up, making the LLM bigger, and assuming that solves everything, it feels like that's winding down now.
It really does. What we saw, and what our research team confirmed across the board, is this huge pivot. The industry is shifting focus
Shifting from the theoretical scaling, the lab stuff, towards what?
towards deploying AI that can actually act
Mm.
autonomously in the
Wow.
real world, both digitally and, physically too. Perceiving, planning, executing complex stuff.
Okay, so it's moving out of the sandbox.
Exactly. It's the shift from the demo phase, the look what AI can do phase, to the production phase. Here's AI actually doing it.
Mm. And you mentioned the research team confirming this.
Yes. What's really fascinating and consistently reported is the focus moving to the entire full stack of AI.
Full stack, meaning
Right. Meaning, it's not just about the fancy algorithm anymore. Leaders are realizing even the smartest model is, well, kind of useless without the whole package working together.
the whole package being.
Three key things, really. You need the silicon, the chips that run it efficiently. You need the solid infrastructure connecting it all. And critically, you need the software frameworks that let the AI actually take action.
Okay. So hardware efficiency meets autonomous software intelligence. That's the convergence driving this moment.
That's it precisely. That's the core theme our research team highlighted again and again this week.
Got it. And our mission today on Tomorrow Unveiled is to, well, cut through all that noise, right? We want to focus on the big shifts, the interconnected ones that are really reshaping AI.
Yeah, and there were four main ones that stood out in the research.
Okay, let's lay them out. First, this rise of AI agents, AI that can think and act for itself.
Second, the hardware breakthroughs making that possible, especially locally on your device.
Third, AI becoming more of a partner in science, tackling really hard, old problems.
And finally, the flip side. The new challenges, the serious risks that come with all this power.
And you mentioned there's some underlying tensions here too, philosophical differences.
Absolutely. We
Yeah.
really need to dig into that. Like in agent development, there's this split emerging. Is it better to build agents using API's structured connections for reliability?
Okay, the API first way.
Or do you go GUI first?
You dad.
Let the AI just look at the screen and click things like a human, aiming for universal compatibility.
Interesting trade-off. Reliability versus universality.
Exactly. And then there's this seemingly technical story about memory chips, HBM.
High bandwidth memory, right.
Right. But the supply of that stuff, it directly impacts the cost and feasibility of pretty much every major AI project for the next few years. We need to connect those dots.
Okay, lots to unpack. Let's start with the software then. If the game is shifting from who has the biggest model to who deploys fastest, these new AI agents seem like ground zero. So this idea of an AI agent, it's not science fiction anymore, is it? Software that takes a goal, breaks it down, finds tools, makes a plan, executes it autonomously.
Not at all sci-fi. And this week was proof. We saw multiple major players launching their own frameworks for building these agents almost simultaneously. That's a huge signal the industry is trying to standardize this.
Okay, who made the big moves?
Well, the first one our research team flagged was OpenAI's Agent Kit. This really plants a flag for the API-first approach to automation.
API first, meaning it relies on pre-built connections to other software.
Exactly. Secure, defined connections. And OpenAI is leveraging its massive user base, 800 million weekly users on ChatGPT.
Yeah, something crazy like that.
They're positioning that platform as the foundation, like an operating system, for building these AI agents and apps.
An agent kit is the toolkit for that OS.
Pretty much. It's a whole suite designed to standardize how you build these things. Not just a single tool, but a whole environment. The centerpiece, according to the research, is the agent builder.
Agent builder. And the analogy the team used, I like this. It's like Canva for building agents.
That's a great way to put it. It really streamlines things. It's a low-code, maybe even no-code visual canvas.
So you can drag and drop parts of the agent's logic?
Yeah, exactly. You map out the workflow visually. If this happens, use this tool, then do that. Connect logic blocks, link tools. You're designing complex, multi-step processes without writing tons of custom code yourself.
That visual aspect must make it way faster for developers, right?
Hugely faster. But for businesses, for enterprise adoption, it's not just about the visual design. Agent Kit includes other crucial pieces.
Like what?
Well, there's ChatKit, which helps embed chat interfaces easily.
Okay.
Saves time on the front-end stuff. But the really critical part for enterprise is the connector registry.
Connector registry. Why is a registry so important? It sounds a bit dull.
Huh. It sounds dull, but it's fundamental for governance and security. Think of it as a central control panel. It manages all the connections the AI agent might need to make to other systems.
Like connecting to company databases or cloud storage?
Precisely. Secure links to things like Dropbox, Microsoft Teams, Salesforce, internal databases. In a company, you can't just have AI agents randomly connecting to sensitive data, right?
Definitely not.
The registry ensures every connection is authorized, it's logged, it's auditable. It brings that enterprise-grade control.
Okay, so the big takeaway here, the why it matters, is speed, developer velocity.
Absolutely. The research team's analysis points directly at that. AgentKit is built to slash development time for robust, production-ready agents.
And we have evidence of that.
Yeah, early adopters, big companies, reported massive productivity jumps, building complex agents for things like procurement or customer support in hours, not weeks or months, cutting iteration cycles by over 70%.
Wow. So the competition isn't just model smarts anymore. It's time to market for these deployable agents.
That's the shift. But okay, just as OpenAI doubled down on that structured API-first world, Google DeepMind dropped something totally different.
Ah, the other side of the coin.
Exactly. Their Gemini 2.5 computer use model. This represents the other philosophy, the GUI-First approach.
GUI, graphical user interface, so it interacts with the screen.
Like a human does. It looks at the pixels, identifies buttons and fields visually, and decides where to click or type. It doesn't need an API.
Whoa. How does that actually work? That sounds complicated and maybe fragile.
It's definitely complex. The core mechanism is this continuous loop, screenshot action loop.
Screenshot action loop.
Yeah. The agent gets a snapshot of the screen, could be a web page, an old desktop app, anything visual. Uses Gemini 2.5 Pro's vision capabilities to analyze that image. Okay, there's a button here, a text field there.
So it's literally seeing the interface.
Exactly. Then, based on its goal, it generates a specific low-level UI command, like click pixel coordinate XY or type text stat XY, some text.
And it executes that command.
Right. The system clicks or types. Then, instantly, it takes another screenshot to see the result. Did the screen change? Did a new window pop up? And the loop repeats. Analyze, act, analyze, act.
That allows it to navigate through steps, even across different apps.
That's the idea. It navigates complex workflows just by looking and interacting step by step.
Okay, I can see the power here. This is what you meant by unlocking the long tail.
Yeah, precisely. The research team emphasized this point. Think about all the legacy software out there, especially in big companies. Mission-critical internal tools built years ago. They don't have nice, modern APIs for AI to connect to.
So AgentKit wouldn't work easily there.
Not without significant extra work, no. But this Gemini computer use approach, it works through the glass. It can automate tasks on literally any visual interface, stuff that was previously impossible to automate with AI.
So we have this clear philosophical split then. OpenAI's AgentKit, API first, aiming for reliability, security, predictable structure. Google's computer use, GUI first, aiming for universality, working on anything visual, even if it's maybe a bit slower or less predictable sometimes.
That's the core tension the research highlights. OpenAI prioritizes the structured path. Google prioritizes the work anywhere path.
Which one wins?
Honestly. The consensus from the analysis seems to be the future probably needs both. A hybrid approach. Use APIs when they're available for speed and reliability, but switch to visual navigation when you hit a wall, like with legacy systems.
Makes sense. Adaptability is key. Okay, let's talk about an agent that needs both reliability and adaptability, maybe at the extreme end. CodeMender.
Ah, yes. CodeMender. Another one from Google DeepMind. And this one moves AI way beyond general chat into a super specialized high-stakes role.
Which is?
Essentially an autonomous security engineer. Our research team looked into this. CodeMender doesn't just find security vulnerabilities in code, which is hard enough.
It does what?
It proactively generates fixes, validates that those fixes actually work and don't anything else, and then automatically submits them as patches.
Wait, it writes and submits code changes to fix security holes. Autonomously, that's bold.
It's extraordinary. And the validation part is key. It can't just suggest a fix. It has to be sure.
How does it get sure? Fixing one bug could easily create another, right?
Absolutely. That's the core engineering challenge they tackled. It uses really advanced techniques. First, program analysis to find the bug's root cause. Then it generates potential code patches.
Okay.
Then comes the rigorous testing of its own proposed fix. It runs static analysis, dynamic tests, actually running the code, and something called fuzzing.
Fuzzing.
Yeah, throwing millions of weird, unexpected inputs at the patched code to try and break it to make sure it doesn't introduce new problems
Yeah.
known as regressions.
Only if the patch survives all that testing.
Only then does it get submitted. The real-world impact here, according to the research, is already significant.
How so?
In just 6 months of testing on major open-source projects complex, widely used code bases, CodeMender contributed 72 validated security fixes.
72 actual fixes deployed.
Validated and accepted by the human maintainers, yes. It's demonstrating this proactive, preventative security capability, fixing vulnerabilities before they're ever discovered or exploited by attackers.
Like an AI immune system for software.
That's a good analogy. Analyses showed some of its fixes, like adding better checks on data boundaries, could have prevented major real-world security breaches that happened in the past year if they'd been in place earlier.
That's massive potential scale. But the trust factor must be huge, letting an AI modify critical code.
It's the central issue. The research team stressed that the whole approach relies on a very strict human-in-the-loop process for now. The AI's validation is incredibly tough, so only the highest quality, safest patches even get presented for human review.
So the AI does the heavy lifting, finds the fix, proves it's safe, but a human gives the final okay.
Exactly. The bottleneck isn't the AI's capability anymore. It's building the governance, the processes, and frankly, the human trust to let these systems operate on critical infrastructure.
Okay, so we have these increasingly capable agents, whether they're using APIs or looking at screens or even fixing code. But all this complex thinking, especially in real time, it needs serious horsepower, doesn't it?
Absolutely massive amounts. And crucially, it often needs that power locally, not just in some distant cloud data center. This brings us right to the physical foundation, the hardware.
Right. Segment 2 is all about the infrastructure enabling these agents, the move away from the cloud, and also tackling a big bottleneck in the supply chain.
You really can't separate the software advances from the hardware. That symbiotic relationship is clearer than ever. Think about those GUI agents constantly processing screenshots, or imagine an AI agent running on a robot interacting with the physical world.
Yeah, you can't have lag. Sending that data back and forth to the cloud would be too slow, too expensive, maybe not private enough.
Exactly. Latency, cost, privacy, all big issues. Which means AI has to move closer to the edge, onto the device itself.
And that leads us straight to the concept of the AI PC. This week, Intel made a big splash here with their Panther Lake architecture, right?
A very big splash. This isn't just a minor chip refresh. Panther Lake is built on Intel's most advanced process node yet, the 18A node. And it's a big deal not just technically, but also strategically for strengthening semiconductor manufacturing in the U.S.
18A, what makes that node so special?
It brings two major industry-first technologies to mass production. First is RibbonFET.
RibbonFET.
Yeah, it's Intel's version of a new transistor design called Gate-All-Around, or GAA. Think of it as a complete redesign of the chip's fundamental switch. It controls electrical current leakage much better than older designs like FinFET.
Better control means more efficiency, less power wasted.
Exactly. Better power efficiency, and it helps the transistors keep shrinking, following Moore's law, sort of.
Okay, that's one. What's the second big tech in 18A?
The second one sounds even more radical. Power via. This is about how power is delivered to the transistors.
How does that change?
Traditionally, the tiny wires carrying data signals and the wires delivering power all run on the front surface of the silicon chip, kind of crammed together. Power via physically moves the power delivery network to the back of the wafer.
Whoa! Separating the power lines from the data lines.
Precisely. Imagine separating a highway's traffic lanes from its power lines and plumbing. Less interference, less resistance. It allows for better performance and lets you pack transistors even more densely on the chip.
Okay, RibbonFET for efficiency, power via for performance and density. How does this translate back to running those AI agents we talked about?
This is where the specs matter. The research confirms Panther Lake architecture includes a seriously beefed up AI engine, a dedicated neural processing unit, or NPU, and it's capable of delivering up to 180 platform TOPS.
TOPS, trillions of operations per second.
Right, 180 trillion AI calculations every second, happening right there on your laptop or PC. That's a massive leap in local processing power.
Okay, 180 TOPS is a big number, but why is that specifically important for, say, a GUI agent like Gemini computer use?
It comes back to latency, cost, and privacy. If that GUI agent had to send every single screenshot up to the cloud for analysis, what button is this? Where should I click?
Yeah.
The delay would make it feel sluggish, maybe unusable for fast tasks.
And the cost of constantly sending and processing those images in the cloud would add up fast.
Astronomically fast. Plus, do you really want screenshots of everything you're doing constantly streamed to the cloud? The 180 TOPS NPU lets that complex visual analysis, that AI thinking, happen right there on your device, instantly, privately, and without racking up cloud bills.
So Intel is building the client-side platform needed for this next wave of autonomous personal AI, solving those core issues.
That's exactly the strategy. It's proactive hardware enablement for the software revolution we're seeing.
That vertical integration makes sense. But okay, even with powerful AI PCs, the really heavy lifting, like training these giant models in the first place, still happens in the cloud, right?
Oh, absolutely. Training frontier models requires massive data centers.
And for what, over a year now, our research has been pointing to a major bottleneck holding back the performance and even the production of the most powerful AI accelerators in those data centers.
Yes, the infamous memory bottleneck. Specifically, the supply of high bandwidth memory, HBM.
Explain HBM again quickly. It's not like regular computer RAM.
Not at all. HBM involves stacking multiple layers of specialized memory chips very close to the main processing chip, the GPU or AI accelerator. This allows for incredibly fast data transfer between the memory and the processor, which is absolutely critical for feeding these data-hungry AI models.
But making these stacked HBM chips is hard.
Extremely hard, getting the layers perfectly aligned, managing the heat, meeting the incredibly strict quality standards demanded by companies like NVIDIA. It's incredibly complex manufacturing. This difficulty created, effectively, a duopoly in the HBM market for the latest generation.
Meaning just two main suppliers could reliably make the good stuff.
Pretty much. And that limited supply couldn't keep up with the explosive demand from AI, which constrained the production of accelerators and drove up costs significantly.
Okay, so what was the breakthrough this week?
The big news, corroborated by our research team, is that Samsung Electronics finally got the green light. They secured NVIDIA's qualification for their latest 12-layer HBM3E chips.
After struggling for a while.
Yeah, reports indicate it was a tough 18-month process for Samsung to consistently meet NVIDIA's exacting quality and thermal requirements for this cutting-edge memory, but they finally crowned it.
And why is Samsung getting qualified such a big deal?
Because Samsung is a manufacturing giant. Them entering the high-end HBM3E market in full force immediately breaks that effective duopoly and promises to bring massive new production capacity online.
What kind of performance are we talking about with this HBM3E?
The specs are impressive. Samsung's 12-layer HBM3E offers 36 gigabytes of capacity per stack and, crucially, bandwidth up to 12,280 gigabytes per second.
1,280 gigabytes. That's incredibly fast.
It's the speed needed to keep those powerful AI accelerators fed with data, allowing them to run at peak performance without starving for information.
Okay, so the bottleneck is easing. What's the so what for everyone else? What's the economic impact?
It's potentially huge. The HBM shortage was arguably the single biggest factor inflating the cost of building AI accelerators. More supply means more competition and lower component costs. The projections our team analyzed suggest this could lead to a 15 to 20% reduction in overall AI training costs by late 2026.
Wow, 15–20% lower training costs. That's significant.
Very significant. It makes AI adoption more affordable across the board, from startups to large enterprises. And just as importantly, it enables the next generation of even larger, more powerful frontier models.
Like the rumored GPT-5.
Exactly. The development of models like that has been fundamentally constrained not just by algorithms, but by the physical availability of enough HBM and compute power. Breaking the HBM bottleneck doesn't just lower costs, it literally unlocks the next phase of AI model innovation. It's a supply chain story with massive ripple effects.
If you're finding this insightful, please take a moment to like this video, subscribe to Tomorrow Unveiled, and consider hitting that new hype button to help us reach more viewers. And of course, be sure to turn on notifications so you never miss an update on the future. And if you're listening on a podcast service like Apple Podcasts or Spotify, we'd be incredibly grateful if you could leave us a rating and review for Tomorrow Unveiled. It truly helps us reach new listeners and keeps this deep dive moving forward. All right, moving on from the hardware and the supply chains, let's talk about something maybe even more profound. How AI is starting to make genuine breakthroughs in fundamental science, solving problems that have stumped humans for centuries.
Yeah, this is where AI shifts from being just a tool for deployment or automation to becoming a true partner in discovery. It's pretty exciting stuff.
And a key driver here seems to be this new approach called physics-informed neural networks, or PINNs.
That's right. PINNs represent a really elegant shift in how we train AI for scientific problems. The traditional way is, just throw massive amounts of data at a neural network and hope it learns the underlying patterns, the physics, implicitly.
Kind of like learning by example, but millions of examples.
Exactly. With PINs, you take a different route. You actually encode known physical laws, things like conservation of energy, conservation of momentum. The rules we already know govern the system directly into the mathematical structure of the neural network itself.
So you're giving the AI a cheat sheet. Hey, remember, energy can't be created or destroyed while you're learning this.
Huh. Sort of, yeah. It's less a cheat sheet and more like building the rules right into its foundation. This dramatically narrows down the possible solutions the AI considers. It forces the output to be physically consistent and meaningful from the start.
And the big advantage is
Two main things. First, you often need way less training data because the AI isn't starting from absolute scratch. It's leveraging known physics. Second, the predictions it makes are usually more accurate and physically plausible, which is critical for science and engineering.
okay, less data, more accurate results, and we saw some major breakthroughs using PNNs this week.
Absolutely stunning ones. Let's start with breakthrough one, the century-old fluid dynamics problem. Our research team highlighted work from Google DeepMind using PNNs to study the Navier-Stokes equations.
Ah, Navier-Stokes. Those are the incredibly complex equations that describe how fluids flow, right? Like air over a wing or water in a pipe.
Exactly. And finding a complete general solution to them is actually one of the Clay Mathematics Institute's Millennium Prize problems, a $1 million prize for solving one of 7 fundamental math challenges.
So, did the AI solve it? Did DeepMind win the $1 million?
Not quite. It didn't find the full general solution. But what it did do, using PINs, was discover entirely new families of specific mathematical solutions, describing phenomena called singularities within the fluid flow.
New solutions that mathematicians hadn't found before.
Verifiably new solutions, yes. And this is historic. It's reported as the first time machine learning has discovered genuinely new, non-trivial, verifiable solutions to these famous, complex, partial differential equations.
So the AI isn't just crunching numbers faster, it's providing fundamentally new mathematical insights into physics.
That's the leap. It's moving from computation to discovery. The implications could be huge for things like designing more efficient aircraft, understanding turbulence better, or creating much more accurate long-range weather models.
Wow, okay, that's fluids. What else?
Breakthrough 2. Materials science acceleration. This involves trying to discover new materials with desirable properties, lighter, stronger, better conductors, etc. The challenge here is the sheer number of possibilities.
Right, figuring out how all the atoms might arrange themselves and what properties result. It's computationally insane.
Exactly. It's called the curse of dimensionality. The complexity explodes. Our research team flagged work from Los Alamos researchers who developed a new framework called Thor tensors for high-dimensional object representation.
Thor. What does it do?
It uses a mathematical technique involving tensor networks combined with AI to compute these complex statistical mechanics problems, the physics underlying material properties, incredibly efficiently.
How efficiently?
Get this, 400 times faster than traditional supercomputing methods while maintaining the necessary chemical accuracy. Calculations that used to take weeks on a cluster can now be done in seconds on a single GPU.
Weeks to seconds. That completely changes the pace of discovering new materials, doesn't it? For batteries, superconductors, anything.
It absolutely accelerates the discovery pipeline. But maybe the most striking example of the power of physics-informed approaches came from KAIST researchers.
This is breakthrough 3, minimal data discovery.
Yes. They used physics-informed machine learning, PML, a similar concept to PNNs, to predict the properties of 60 entirely new materials.
Okay, how much data did they need to train the AI?
This is the amazing part. They trained the system on just 20 known examples.
20.
20 examples to predict 60 new materials accurately. How is that even possible?
Because the AI wasn't just learning from those 20 data points, it was learning within the constraints of known physical laws embedded in its structure. It leverages centuries of accumulated physics knowledge, allowing it to generalize incredibly effectively from very sparse data. That's the magic of the physics-informed approach.
That efficiency is mind-blowing. Okay, AI tackling classical physics is impressive. But what about the ultimate frontier, quantum computing?
Ah, yes. There was a major hardware milestone there too, highlighted by the research team. This one came from Harvard researchers.
What did they achieve?
They demonstrated the first continuously operating quantum computer.
Continuously operating. What does that mean? I thought quantum computers were notoriously unstable. They are. That's the breakthrough. Usually the quantum state, the qubits, decay very quickly, often in fractions of a second, limiting calculations. This Hartford system ran complex operations for more than 2 hours, using around 3,000 qubits.
2 hours? How did they manage that?
They developed really ingenious techniques using lasers, things they call optical lattice conveyor belts and optical tweezers, to essentially trap and continuously replenish the atoms being used as qubits before they could decay or get lost.
So they solved, or at least dramatically reduced, the atomic loss or decoherence problem that plagues quantum computing.
They made a massive stride in mitigating it, yes. It removes one of the biggest physical roadblocks. And the researchers involved, along with collaborators, are now projecting that this could lead to truly autonomous, reliable quantum computers much faster than previously thought.
Not much faster.
Their projection, noted in the research, is potentially within 3 years. That's a dramatic acceleration of the timeline.
3 years for reliable quantum computers. Wow. And how does this connect back to AI?
It creates this incredibly powerful potential feedback loop. Mature quantum computers could unlock types of calculations relevant to AI, like optimization problems, material science, drug discovery, that are simply impossible for classical computers, potentially supercharging AI capabilities.
And the AI helps the quantum computer.
Exactly. In return, the advanced AI models and agents we've been talking about are already being used to help design better quantum algorithms, optimize the control systems for the quantum hardware, and perform error correction. The two fields are starting to really push each other forward.
Okay, this is all incredibly powerful. Agents acting autonomously, chips with 180 TOPS, AI solving fundamental physics, quantum computing potentially just years away. But with great power comes
Great responsibility.
Hey.
And great risks. Absolutely. We have to talk about the critical challenges because they are escalating right alongside the capabilities, and the threats aren't just in the software anymore.
Right. Let's start with novel security vulnerabilities. Our research team flagged a worrying one at the hardware level.
Yes, a new type of hardware side channel attack being called gate bleed.
Side channel attack. Remind us what that is.
It's where an attacker doesn't find a bug in the software code itself, but instead exploits the physical characteristics of the hardware as it runs. They might monitor tiny variations in power consumption, timing of operations, or even electromagnetic radiation coming off the chip.
And they can learn secrets from that leakage.
Potentially, yes. With gate bleed, the research showed that by carefully monitoring the timing and the power, draw patterns of specialized AI accelerator chips.
The kind used for deep learning.
Exactly. An attacker, perhaps with just limited access on a shared cloud server, could potentially infer sensitive information being processed by that chip.
What kind of information?
It could be anything from the proprietary training data used to build the AI model to the specific structure or weights of the model itself, or even real-time user inputs being fed into the AI.
That's terrifying. It means security can't just be a software layer anymore.
Precisely. This confirms that AI security has to be designed right into the silicon itself. You need hardware-level defenses against these physical side-channel attacks. Otherwise, the core intelligence of the AI could potentially be stolen just by watching the chip operate.
A huge challenge for chip designers and cloud providers. Okay, that's hardware. What about the software and data side?
The other major vulnerability highlighted is the data supply chain attack, often called poisoning. Researchers demonstrated just how easy it can be to corrupt the data used to train large language models.
But these models are trained on trillions of words, right? Wasn't the idea that the sheer scale of data would dilute any bad apples?
That was the hope. But the research indicates it's a flawed assumption. One study showed that injecting as few as 250 malicious examples into a massive training data set.
250 out of billions or trillions, that's tiny, like 0.00016%.
Exactly, an almost undetectable amount. Yet it was enough to consistently corrupt the resulting model's behavior, making it respond maliciously when triggered by a secret phrase known only to the attacker.
So you could implant a hidden backdoor into a major AI model trained by a big company.
That's the demonstrated risk. A subtle trigger could make the AI suddenly output dangerous code, biased information, or extremist content on command. It shows a critical weakness in how training data is currently sourced and validated.
Model builders need much better ways to track where their data comes from and clean it rigorously.
Urgently, yes. Data provenance and sanitization just became even more critical.
Beyond these direct security threats, there are the broader ethical and bias amplification issues, which seem to get worse as the AI gets more capable.
Definitely. The rise of hyper-realistic generative models, like the updated Sora 2 video model mentioned in the research, is fueling what some are calling a crisis of authenticity
Deepfakes getting harder to spot.
and easier to create and deploy maliciously. The research pointed to examples this week of sophisticated deepfake videos being used to intentionally stir up social unrest, targeting specific communities or political groups.
AI-generated misinformation that looks completely real.
Exactly. Which creates an urgent need for better deepfake detection tools, but also stronger legal and social deterrents.
And the ethical issues hit the creative industries too, right? The whole copyright conflict.
Yes, that debate continues. Sora 2's reported policy, where content creators apparently have to actively opt out of having their work, scraped from the web, used to train the AI, remains highly controversial.
So the default is the AI can use your stuff unless you tell it not to.
That seems to be the model, and critics argue it puts an unfair burden on creators and essentially appropriates vast amounts of creative work without clear compensation or consent. It's a major point of friction.
And then there's the persistent problem of societal bias. The AI learns from the world, and the world is biased.
And the AI often amplifies those biases. New studies highlighted by the research team continue to show this. For example, models systematically portraying women as younger than men or associating certain demographics with lower-income jobs and others with higher-income ones, reflecting biases present in online text and images.
And if these biased models are used in the real world, like those enterprise agents for hiring or loan applications,
Then they risk automating and entrenching those biases at a massive scale. Even CodeMender, fixing security bugs, could it introduce bias in which bugs it prioritizes or how it fixes them? It's a serious concern. Actively mitigating bias, ensuring fairness, is becoming just as important as ensuring the AI simply works. #, conclusion and outlook. So if we try to tie all these threads together, connect the dots from this week's news, what the research confirms is really two massive pivots happening at the same time.
okay, what are they?
First, AI is becoming truly autonomous. We see it with Agent Kit, with Gemini computer use, with CodeMender. It's about AI taking initiative and executing plans.
And second,
Second, AI is becoming profoundly physical. It's moving onto the hardware with the AI PC and Panther Lake. It's interacting with the physical world through robotics implicitly, and even tackling fundamental physics problems, autonomous and physical.
and that changes the whole competitive game, doesn't it? It's not just about having the biggest language model in the lab anymore.
Not at all. The research strongly suggests the new competitive advantage, the new moat, is controlling the entire vertically integrated stack. Meaning everything from designing the specialized silicon like Intel's NPU with ribbon FET and PowerVia, securing the critical supply chains like Samsung breaking the HBM bottleneck, all the way up to providing the developer frameworks like Agent Kit or computer use that let people actually build and deploy reliable AI applications on top of that foundation.
So the winners will be those who can orchestrate across all those layers: hardware, infrastructure, models, developer tools.
That seems to be the emerging consensus. It's about building the complete, reliable platform for this next era of AI. Less about pure novelty, more about robust engineering and integration.
It really feels like these technologies are accelerating out of the research phase and into real-world deployment incredibly fast now, maybe even uncomfortably fast.
The speed is definitely breathtaking, and it shifts the fundamental question we need to ask. It's less about, can AI do this amazing thing anymore?
And more about,
Okay, it can do this. Now, how do we deploy it safely, reliably, ethically, and securely at scale, especially given these new hardware and data vulnerabilities we're uncovering? That's the critical challenge now.
we've seen AI agents this week fixing critical security bugs, solving physics problems humans couldn't for a century, navigating complex software just by looking. It's kind of staggering. Which leads to a final thought for you, our listener. If the AI PC running these powerful new autonomous agents is really about to become standard equipment, what's the first truly customized personal AI agent you would build? What's that persistent professional challenge, that annoying task, that time sink you'd want your own personal AI agent to tackle first? We love hearing your thoughts. Whether you're on YouTube or your favorite podcast app, leave a comment and let us know what you think about this week's shift to autonomous AI and the hardware underpinning it all. Thank you for tuning in to Tomorrow Unveiled.